All right, here are a few questions dealing with Boyle's Law, Charles' Law, the combined gas law. So let's just go over these together. Hopefully you've done the problems already and you're just checking your answers now. So question number one, and again, I'm going to share my thought process with you as we go through these. A balloon at 25 degrees Celsius is filled with 2 liters of air at a pressure of 3 atmospheres. The pressure is reduced to 0.5 atmospheres at constant temperature. So right away, whenever I see these problems, I always initially think, okay, start with the combined gas law, and then as you see something that's constant or something that doesn't change, just take it out. So right away when it says constant temperature, I know that I can take out the temperature, so it just becomes a Boyle's Law problem. P1V1 equals P2V2. Okay, so the initial pressure is 3.0 atmospheres. And again, guys, here it does tell you what pressure is, but you have to start recognizing, oh, when it says liters, I know that's a volume. Even though it doesn't say a volume of 2 liters, you need to start using these units here to help you identify, oh, 2.0, that's the volume initially. The pressure's dropped to 0.5 atmospheres, so 0.5 ATM, and they want to know what the final volume is going to be. So I simply take 3 times 2, which is 6. 6 divided by 1/2 is 12. So the final volume would be 12 liters. Okay? And again, the pressure drops by a whole bunch. If the pressure dropped by a whole bunch, it had to have happened. The pressure happened because the volume got bigger, and it did. The volume went from 2 liters to 12 liters. Okay, here's a real-life example of Boyle's Law. Deep sea divers can get what's called the bends, okay? And if you've ever done any research on if you're deep down in the ocean and you come up to the surface, you have to stop every now and then to let your body basically even out the amount of pressure and the volume of the gases in your blood. If you don't, if you come up to the surface too quickly, and again, we're not talking about, hey, I'm swimming at the beach. We're talking about people who have scuba tanks and they're way down there and they come up too quickly. And this happens because the gases in your blood expand and they form bubbles, which can cause some pretty severe pain when those bubbles get stuck in different parts of your body. So let's say Susan, who's a deep sea diver, is at a depth of 50 meters, which is just over 150 feet. In the ocean, and she's under 4,010 torr of pressure. Now that sounds like a lot, but remember, that's torr. That's about 5 atmospheres. The dissolved gases in her blood have a volume of 0.0118 liters. Susan, again, not being too smart here, because she rises to the surface quickly, where the pressure is only about 1 atmosphere. Okay, it should say. Oh, sorry, I messed up there. It should say 1.00 ATM. What will the volume of the gases in her blood be at this new pressure at constant temperature? So again, the temperature is constant. So again, this is a P1V1 equals P2V2. Okay, and so our initial pressure when she's under the ocean is 4,010 torr. The initial volume of those gases in her blood are 0.0118 liters. The final pressure, and sorry, I forgot to put atmospheres in there, is atmospheres, but this is torr, so we want to make them the same. So I'm going to convert my atmospheres to torr, which is 760, and then the volume is our unknown. So to find that volume, we're going to take 4,010 multiplied by 0.0118, divide by 760, and we get a volume of 0.0623 liters. Now, that doesn't seem like very much, but if you think about it, 0.0118 liters is 11.8 milliliters. Okay, so that's the volume of these gases in your blood. And now, by coming up quickly to the surface, you've gone from a volume of 11 milliliters to 62.3 milliliters. You've increased by about over 5 times the volume of the gases in that blood. Okay, and when things expand, think about when water expands, it breaks sprinkler pipes, it breaks glasses if you put them in the freezer. Okay, that can be very, very dangerous. Okay, and that's it. That's all I'm going to say about that, because it kind of leads to this next question, number 3. Let's say, and again, you're not actually at the bottom of the ocean. The pressure's pretty darn high there. There's no way you're just hanging out at the bottom of the ocean. But again, just for the purpose here, you blow a 0.500, so half of a liter a bubble. So you're at the bottom of the ocean, and you're like, and you blow a bubble out. Okay, and it's half a liter big. Okay, the pressure at that point is about 745,000 millimeters of mercury. But of course, that bubble, what's it going to do? It's going to slowly rise to the surface. Once the bubble reaches the surface, the pressure's dropped to just about normal atmospheric pressure, 765 millimeters of mercury. The question is, how big will that bubble be? Or what will the volume of that bubble be once it reaches the surface? Okay, and we're going to talk about how this actually could affect things in real life. So let's see. The pressure, so we've got volume, we've got pressure. We don't see anything about temperature, so we can leave temperature out again. So this is another Boyle's Law question. P1V1 equals P2V2. So the initial pressure is 745,000 millimeters of mercury. The volume is that half a liter. The final pressure is 765 millimeters of mercury, and we want to know how big that bubble's going to be. So 745,000 times 0.5 divided by 765 equals roughly 470 liters. Okay, and you think about like a 2-liter bottle, right? Okay, times that by what, 235. Take 235 2-liter bottles. That's how big that air bubble would become. Now think about, and this question wouldn't really happen, but think about in the bottom of the ocean that absolutely there are vents in the bottom of the ocean where bubbles of carbon dioxide, of different gases are released. And these gases come up to the surface here, where all of a sudden there's this gigantic, a 470 liter volume bubble that all of a sudden comes to the surface. So here's a little boat right out here in the middle of the ocean, and all of a sudden this gigantic bubble comes up and basically pops. And what happens to the boat? Well, all of a sudden all this water's gone, the boat sinks, and now all the water comes in on top of it. Some people think, like in the Bermuda Triangle, you hear about a lot of boats disappearing in the Bermuda Triangle. A lot of people think that might be wise because these really small bubbles at the bottom of the ocean are released, but by the time they get to the surface, there are these gigantic bubbles that when they get there, that it's gone from such a small size to such a big size that these boats are literally sitting there. All of a sudden, there's this huge bubble that comes up underneath it, way, way bigger than the boat. The boat drops down, and then all of a sudden, all this water comes on the top, and the boat sinks. Again, is there any truth to that? Who knows? But that is one possibility of what's happened. Why do so many boats tend to disappear in this Bermuda Triangle they talk about? Okay, let's continue. Number 4, 25 degrees Celsius. The volume of a gas in a car tire is 5 liters at constant pressure. So now the pressure's staying constant. So what do we know right away? V1 over T1 equals V2 over T2. The car is left outside overnight. When it gets extremely cold, you go to drive your car the following morning. It's negative 15 outside. Eesh, that's cold. Okay, what will be the volume of gas in your car tires at 6 a.m.? So our initial volume is 5.00 liters. Our temperature was 25. That's 298 Kelvin. The next morning, it's negative 15. So that's 258 Kelvin. And then what's the volume going to be? It should look like that. We're going to cross multiply. We're going to divide. We're going to take 258, multiply it by 5, and then divide by 298. And our volume comes out to be 4.33 liters. And if you think about it, big deal. That's only 0.7. Well, when you only have 5 liters of air in your tire, and this happens all the time during the winter, is you get the little warning on your dash that says, hey, you need to put some air in your tire. Because absolutely this happens, that when the temperature drops, the volume or the pressure inside of that tire also drops. And so many times in the winter, you have to add more air to your tire to get that volume back up to where it's supposed to be. Okay, a balloon is filled with 6.25 liters of air at room temperature, about 22 degrees Celsius. Constant pressure, again, we see that. So right away, V1 over T1 equals V2 over T2. They then place the balloon immediately into liquid nitrogen, and the volume drops to 2.14 liters. What's the temperature of liquid nitrogen in Celsius? So our initial volume is 6.25 liters. Our initial temperature is 273 plus 22 is 295 Kelvin. Our final volume, they tell us, is 2.14 liters, and we're looking for the temperature of liquid nitrogen. So again, like always, cross multiply, then divide. So 295 times 2.14 divided by 6.25 equals a temperature equal to 101 Kelvin. Okay, remember that's in Kelvin and they want it in Celsius. So now we have to subtract 273 from that. So the final temperature is about negative 172 degrees Celsius. Okay, so liquid nitrogen is real cold. Okay, about negative 170 degrees Celsius. Okay, number 6, we got 2 more here. 2 liters of Freon gas in a freezer at 35 degrees Celsius. So that's pretty warm. That freezer isn't doing too good if it's at 35 degrees. Okay, is brought down to where a freezer is supposed to be at about 0 degrees Celsius. Okay, and the pressure goes from 0.833 atmospheres to 1 atmosphere. So it doesn't change very much, but it changes a little bit. Okay, what is the volume of the Freon gas under these new conditions? So we can see the temperature changing, we can see the pressure changing, and then they're asking about the volume, which means we have to use the full combined gas law. P1 V1 over T1 equals P2 V2 over T2. Okay, so our initial pressure, again, when you think about pressure, it's got to be atmospheres, millimeters of mercury, or torr. So here's our atmospheres right here. So we're going to go 0.833 ATM times our initial volume, 2.00 liters, over our initial temperature, 273 plus 35 is 308 Kelvin. And now our final temperature and pressure are, the pressure is 1 atmosphere, the volume is our unknown, and the temperature is 0 degrees Celsius, which is 273 Kelvin. Okay, so now we're going to cross multiply. So the 273 goes up here, the 308 goes here, and then to get V2 by itself, we're going to have to divide by 1 and then divide by that 308. So in my calculator, I'm going to put 0.833 times 2.00 times 273. Remember that 273 went up here, divided by 1.00 divided by 308. So 0.833 times 2 times 273 divided by 1 divided by 308 equals 1.48. And they're asking for the volume, so that's 1.48 liters. Okay. Now, number 7, our last one. The gas in a hot air balloon. So how do hot air balloons work? Well, the gas in the hot air balloon is slowly heated as they turn on that flame from 22 degrees to 52 degrees. So that's 295, and 273 plus 52 is 325 Kelvin. While the pressure drops from 860 to 780 millimeters of mercury. If the initial volume of the hot air balloon is 950 liters, again, a hot air balloon's pretty big, what will be the final volume of air in the hot air balloon. So again, nothing's staying constant. So we're going to have to use the whole thing. So our initial pressure is 860. So there's our P1. Our V1 is our initial volume. That's 950 liters over our initial temperature, 295 Kelvin. Our final pressure is 780. Our final volume is what they're asking us for. What will be the final volume? And then our final temperature is 325 Kelvin. Okay, so I'm going to do this one. 860 times 950 times 325 divided by 295 divided by 780 equals 1,154 liters. And you think, wait a minute, Mr. Johnson. Hot air balloons, they don't stretch. They don't get bigger or smaller. You're actually right. They don't. Okay, but here's what I want you to think. The total volume is 950 liters, and we need 1,154 liters of space for that air to go into. Well, the air can't get, there's only 950 liters of space. So where do those extra 200 liters of air go? They come out the bottom of the hot air balloon. Well, where do they go? They just go out into the air. Well, so you've basically lost over 200 liters of air. You're right, you have. And what does that do? Well, it lowers the density of the hot air balloon. Okay, it makes the hot air balloon, less dense than the air. And what does that make it do? Of course, it makes it rise in the air. Okay, that's why boats on a river float, because they're less dense than water. So how does a hot air balloon work? It's less dense than the air, because by heating up the air inside of there, the air needs more space. You don't have the space, so the air comes out of the hot air balloon, making the hot air balloon less dense than the air. And then it goes up into the air. Okay? Well, how do they make the hot air balloon come down? Well, they turn off the flame. And when they turn off the flame, the air cools off. And as the air cools off, what does it do? It goes back up into the balloon, making the balloon more dense. And then the hot air balloon slowly starts to descend. And of course, then you add a little bit of heat because you don't want it to descend too fast. Okay? But that's the basics of a hot air balloon is the hot air. We say that hot air expands. It doesn't really expand. It just needs more space. And so it leaves the hot air balloon. Okay? And as it cools off, the cool air goes back in, it makes it more dense, and it sinks. Okay, so that's just a good summary of Boyle's law, Charles' law, and the combined gas law.